And they know, still cleaning up on the road, living fast and sip slow, spending cash to get more. They know, keep a gun everywhere I go, riding around getting dope, living fast and sip slow. They know, still cleaning up on the road, living fast and sip slow, keep a gun everywhere I go. They know, still riding around getting dope, living fast and sip slow.
Took a lot of time and a lot of energy, but I'm finally done implementing the saving and restoring system for my game. So I'll start off by giving a quick showcase of the capabilities of the saving system, and then I'll go into a little bit of detail about how it actually works. So as I mentioned in the last video, this UI here is actually defined in a Python script, and we can go here and see this file demo-window.py. It has a class demo window, which is a subclass of the built-in engine type pf.window, and we can see here this class defines a couple of instance variables, the faction names list and the active faction index, and it has this update method which gets called every single tick, and every time it gets called, based on the local state of the instance, it defines how the UI will look for that tick. So it's an example of an immediate mode UI. And here we can see a couple of method calls. Layout row static. This pushes a row that's 30 pixels tall. And this next call, button label, adds a button to that row with the label settings. And when it gets called, it invokes this onSettings function, which in turn fires this global event settings show, and we can map that to the UI here. So this button, that's we see it basically, the script gets called every tick, and then this button is here. And similarly, these units are completely customized via Python scripting. So we see this here, this class mage, and this class defines what animations get played in all the different states of the mage units, as well as the speed, the armor, the damage, the health points that the mage units have. And the reason I'm saying this is because in the saving system that I've implemented, the complete scripting state actually gets saved, and in turn it gets loaded when we load the session. So let's see a quick example. So I'm going to save the current session to a file test.pfsave. Then I can move these units around, and when I load this session, it gets loaded paused because that's how I programmed it, but all the units got loaded, and all these mage units, they have all the exact same behaviors, they play the same animations, and they have all the exact same attributes that they had before. Similarly, this window, it looks exactly the same, it has all the same behaviors, and the way that works is because this class, the mage class, actually got saved and restored as part of the session. And similarly, all the mage units, when they got restored, all of their instance members got restored as well. Similarly with the window, this local state, faction names, and the active faction index, they got restored as part of the session. And let's just see a quick example of it. So say I select this goblins faction, save it to a session, and then select a different faction. Now when I load the session, this selection is restored to what it was. And now there isn't any custom code for that. The reason that's done is because this member of the demo window instance, active faction index, actually gets saved as part of the saving process and restored as part of the loading process. And all the behavior of the windows is intact, because actually the bytecode of this method update also gets saved and restored. And actually, let's see an even more sophisticated example. So I've opened this editor, which is defined by a completely different script. So as you can see, it doesn't have this demo window UI. It has a completely different UI and a completely different set of event handlers, and just overall completely different behavior. Similarly, I can save it to a file, editor.pfsave. But now comes the most sophisticated part. I'm going to try from within the editor to load the demo session that I saved earlier to test.pfsave. And just like that, I'm back in my demo session. The units are exactly where they were. This UI is, even though it wasn't part of the editor script, so it was never created in the editor. Similarly, this mage class was never interpreted as part of any of the editor scripts. But here, when I'm back in my session, the mage units are exactly as they were, because actually the class and all the bytecode of all the methods of the class are saved and restored as part of the session saving process. And the advantage of this is it's a completely universal approach. So in my game, I plan to have many different missions, and the different missions are going to have different UIs, different units, and even completely different gameplay, which is defined by the event handlers and all the logic that's scripted in Python. And I don't have to write this tedious, saving and restoring session code for every single mission. I have this one universal approach that lets me take any snapshot of the engine, save it to a file, and now let's from here we started the engine by interpreting the editor script. Then we saved it to a file, editor.pfsave. Then right from there, without restarting the engine, we loaded this demo session. Now let's go again, load the editor session. And I'm in the editor, exactly with the same units, the same terrain, everything is exactly the same. And now from here, let's go back to the demo. And I'm back here. So in the next part, I'll talk a little bit about how I actually implemented this system in the code. So stay tuned. So here's a top level code where I saved the Python state, and basically this type, Python interpreter state, inside of CPython, this is the top level struct which defines the interpreter state. And in a nutshell, it basically has three things: the list of all the live modules, the sysdict, which is the dictionary that has all the sys module members, and the built-ins module. And everything else is just some implementation details. These three things are really the meat and potatoes. And as you can see here, what I really do is just take this top level state and traverse it and save it to a file along with all the Python defined event handlers. And the way that looks is, for example, this modules PyObject is a list of module objects, and a module object looks like this. Is really nothing but a dictionary object, or like a wrapper around a dictionary object. And the dictionary object has, you know, 3 special fields: the name, doc, and the package. So name must always be a string, doc and package, they may be none. And actually this type by module object, this struct is not exposed as part of the API. So to implement this system for saving the state, I actually had to go into all these different header files and look into the private member fields. So PyModule object is one of the objects. This function object is another one of the interesting ones. So for example, this function object has this func code field, which is actually an instance of a code object, and the code object itself has this code field, and this field is a byte string of the actual byte code. So when Python script gets interpreted, when it sees a function definition, it will create this code object. So basically I take this code object and I save it as part of the saving process, and the saving process is actually based off the pickling system in Python. And in a nutshell, what that system does is basically traverse the object graph and memorize all the objects for handling the reference cycles, and then basically for every different type of object it emits an instruction. So basically it takes an object graph and converts it into an instruction stream, and during unpickling, this instruction stream is used to recreate the object graph. But the problem with this existing pickling implementation in Python is it's kind of it's limited. It's completely like the pickle module is actually itself is a Python script, so it can't look into all these implementation details that kind of are necessary to have a system that's very universal and robust. So basically what I did was take the exact same approach but extend it by a lot, and I basically added custom handling for all the built-in objects in Python. And actually within my engine I save about 80 or so different of the Python built-in objects, and I save them by giving custom handling to every single one, and that way by just looking into all the fields. Like for example, this py function object, when I see an instance of it in the object graph, I save every single one of the member fields. So the code, the globals, the defaults, the closure, the doc string, the name, the dictionary, and the module attribute. This recref list is recreated separately, but it is handled. So here we can see this file save.txt. This basically is a trace of how the session is saved. So I start off with this top level, which is this list. So this is this is actually the top level tuple that gets saved, and we can see it here in script.c. So it has 8 fields, basically all the PyInterpreter state members and the Python defined handlers. So I basically take and I traverse it, do a depth first traversal using going into all the private struct fields, like in the example of the module, going into this md_dict, and in the example of function object, going into all these members here. In the example of the code object, also going into all the members, and even saving these integers here, like the arc count, the number of locals, the stack size, and so forth. And basically just saving this one session, there's basically around a little less than 27,000 different objects that I touch during the pickling process. And each one, basically when I save the objects, they're converted into an instruction stream, and this is what the instruction stream looks like when I unpickle the exact same session. And we can see the different kinds of opcodes, like for example this built-in. Here's another detail. So one part is the objects, is all the different objects inside of CPython, but there's also some built-in functions. So within CPython, for example, there's like the dir function or the type function. Well, type is, there's some built-in types and there's built-in functions, and there basically are, the built-in types are implemented as a C struct with some populated members, and the built-in functions is really just, you know, a wrap around a function written in C. So I obviously can't really save those by you know, saving the instructions or anything like that. So the way those are handled is at the beginning, when I start the engine, I build an index of all the built-in types, and when I save the built-in types, they're just saved by reference, and during unloading they're fetched from the index. So here we see this instruction pf built-in. This will just, you know, fetch a specific built-in from the index and return a new reference to it. This put takes this string, creates, you know, a brand new string object. This put instruction puts it in the memo, so that later, if there's multiple references to one object, or there's like cyclic references and things like that, there's this get instruction, so that basically all these complex relationships in the object graph get saved. And this instruction stream for unloading one engine session is actually a little less than 170,000 instructions. So that's it in a nutshell. I hope you guys enjoyed the video, and there's going to be a lot more content like this in the future, so subscribe.
Don't sleep cause I won't slip, won't lose cause I won't quit. Life is hard, yeah, no shit, but I'm a real nigga, so I don't